Welcome to the third part of this tutorial series on database querying in R. And now we are actually going to get into a database. We're going to be using SQLite, which is a lightweight database you can run locally on your computer, just so that we have something to play around with, mess up, delete, and not worry about changing anything in an actual quote-unquote important database like the PSA on-farm database. I could go to the command line and type these commands and create a database. So I'm going to go to the terminal and I'm going to type SQLite 3 experiment.db, and it'll show that I'm now at the SQLite command line. It changed from the regular terminal to the SQLite command line. I can look and see what tables are in this database. There are no tables because we just created it. And I can see what instructions happen to create the database. This is sort of the SQL that's happening on the database side. But again, this is not super useful. You kind of have to know exactly what you want to type. There's no clues or hints, and so I find it, really challenging, and so I'm not going to recommend that you do this. So we are actually going to quit out of that, and we are going to go and do it inside R. And so I'm going to switch over to RStudio, and then we're going to talk about how databases work. Like I said, this same document is available as an R notebook, which I have here in RStudio. Again, you can see the header and the intro text, the commands that we just typed, and so now I'm at the same position, this inside R header, that I was on the web page. So first I've got this cleanup chunk that just says, it looks for if there's already any existing data, and we want to run that and make sure that it is all cleared out in case we have any side effects. And then we load the RSQLite package, and then we create a connection object by using dbconnect with the SQLite driver and the name of our database. So this is doing exactly the same thing that we just did at the command line. A couple of notes, this con object we just created, this connection, is super important. It's basically how R knows how to talk to the database. So if I investigate what's in it, we can see that it's a SQLite connection. It's got its path built in. There's a whole bunch of methods for it, but you shouldn't need any of that. It's just that all the commands that you use to operate on the database need to have this connection object associated with them. It's a good idea when you are done working with the database to make sure to disconnect. It's not really going to be a problem at the scale that we're working, but it is true that just like leaving connections open can eventually crash your memory or crash the database. So it's just a good idea to run db disconnect on your connection when you're done using it. An additional note is that you can't save these connections like in your R work session, so you have to reconnect to the database at the top of your script every time you open up R. So, if I were to close this and come back tomorrow, I need to run this same line again about dbconnect. So now we have this empty database that is stored as a file in our working directory. You can see that it is here if I type the list of files that are in my working directory. I've got everything that you see in the GitHub folder, as well as right here, experiment.db, right there. But again, it's empty because we just created it. So let's create some data frames. Here we've got treatments and yields, just like we had in our previous example. So I'm going to run this chunk. And we see that it produced no output because we're just doing an assignment. But now we have these two data frames to work with. So you can run arbitrary SQL inside R. So for example, this is a valid SQL statement. Create table treatments. You give it the name of each column and the type of data that goes into each column, and then you run it using db execute. Again, using this connection object so that R knows how to talk to the database. And then, if you wanted to, that just creates the table. Then you have to actually put your values into the table. Use insert into for that. And you have this sort of like nested function call here so that you can fill in each row with the appropriate data. So if I were to run this chunk, you see that the output is 0 because the first one creating the table created 0 rows, then 8 because we inserted values into 8 rows, and then this db get query on the SQL query select star from treatments gives us this local data frame back, this plot ID, crop, and tillage, and all of our data. I find that really hard to read, so I use some of these shortcuts that kind of construct the SQL for us. So an example is db write table. So it combines the create table and insert into one statement. And then if we run this, you'll see db write table con yields takes our yields object that we have inside R, talks to the connection over con, and then makes a table called, quote, yields, and puts it in there. And then db read table takes our connection and reads the table called, quote, yields. And again, you can see it returns our data that we just put in there. A really important function to kind of explore a database is this list tables. So you can see it just takes the connection object as its only argument, and it gives you back a list of what the names of the tables are. So again, you saw that at the command line I typed .tables, and this is the same output that you would get. I just showed you how you could use an explicit query with db get query and something like select star from treatments, as well as db read table. But I find that this is a little bit cumbersome, especially if you're dealing with large tables. And so one of the really great functions of a database is that you can send it a query and only get back a preview instead of getting back all of the rows that would match that query. And so you usually would split this up into something like send query, and then you fetch some of the rows of that query. And so you can see what happens is we sent the query select star from treatments, and then we fetched the top 5 results just to see what it is. And you can see that it says incomplete. But then we want to look at this preview and figure out, is this actually what we want? It looks like it is. So then we get the remaining rows out of this query, again using db fetch, and then bind together what we got before and then what's left over, and then we have to clear the result before the database will start responding to us again. This is a really complicated pattern. I feel like I didn't explain it terribly well because I always get tripped up on it. It's really annoying having all these intermediate function calls and intermediate variables. It's a really common source of errors. I really don't recommend it, but if you have a really complex SQL query that you want to kind of build up, line by line, this is the way to do that. So what I recommend instead is using tidyr style for your query management. And so this is what I was talking about with dplyr and dbplyr. So let's go ahead and load those. And you can see that we have loaded dplyr, we loaded dbplyr, and then we ran tbl or tibble, and then again passed in the connection object and asked for the treatments table. And so this is kind of interesting output. We see that it has this table treatments at the top, and then question mark by 3 columns. And it tells us what the source of our data is coming from, this SQLite database, and where it's stored in experiment.db. And again, returns the object. So this is what's called a lazy query. It is telling us that it hasn't returned everything. This is like that preview. It only gives you a little taste of the data so that you're not wasting time waiting for the database to return lots and lots of rows. And then you can really quickly build up a complex query, not just, give me all the rows in the treatments table. So for example, if we wanted to look at only the rows that match the corn plots, we would run this TibleCon treatments and then filter, which again I mentioned in the previous tutorial. Filter is for selecting rows out of however many rows that you have. So here we're just using strict equality where crop equals corn. You can see it only returns 4 rows. And you can see at the top now, instead of table treatments, it says that it's a lazy query. What we've done is we've generated a temporary table inside the database. And you can see what the actual SQL being generated is if you use this show query function. So again, we're calling tibble on con treatments, then we're filtering it where crop equals corn, then we want to show the query that is being sent to the database. So select star from treatments where crop equals corn. So that is pretty straightforward SQL syntax. We're going to see pretty soon some much more complicated syntax. So that is coming. In terms of this filtering, you can do this strict equality on this text like I just did. You can also do numeric filters. So here I'm looking at the yields table and I'm looking for where yields are less than 5. And you can use kind of any complicated set of conditionals that you want there. You could be like, oh, where yield is less than 5 and yield is greater than 3, or whatever. And again, that's the same as this vanilla SQL query where select star from yields where MGHA is less than 5. Another common thing that you might want to do inside the database instead of in your local machine is something like a group summary. So here we are asking the database for the treatments table, and then we're grouping it by these 2 treatments, crop and tillage, and then tally is saying, give me the number of rows that you have. And again, we can see that this returned a lazy query where this is still a temporary table in the database. So it hasn't sent everything back to our local environment yet. And you can see what is actually being sent with show query. And you can see that it is getting to be a little bit more complex. You need to know what the names of all these functions are and in what order they go. But this is still manageable to write by hand. However, there are some functions that don't directly translate to SQL. These you have to run inside R itself. For these, you have to make a lazy query and then force it to execute fully and return all of the rows back to your local environment. And the function that you use for that is called collect. So we're going to ask the database for the treatments table, then we are going to collect all the results. Then we're going to use mutate, which again adds new columns to a table. And we're going to say that we want to convert the tillage column to title case, and we want to calculate out what the rep number of the blocks in our experiment were. So we see that we run this, and it's the same 3 columns that we had before, but now we have these 2 additional columns. Label, which is just converting tillage to uppercase, and then rep, which is the first digit of our plot ID. And you'll also notice that this output looks different. Now it doesn't have this lazy query up at the top here, and it tells us explicitly we have 8 rows and 5 columns. You could try running this without the collect statement, and you'll see that we get kind of a confusing error, which, oh my goodness, I don't know what any of these functions are. This is all happening on the back end. But it's saying object tillage not found, and I know that tillage exists. So this is a good clue when you see an error like this and you're messing with databases that some function can't be directly translated into SQL. If you want to see what functions can be directly translated into SQL, there's this really great article, which I would recommend that you have a look at when you're playing around with all this. So now we're going to get to kind of the most complicated thing that databases know how to do, which is joins. And so it's really difficult to explain how joins work without some graphics. So there's lots of places that you can Google around and look at the various diagrams that joins refer to, which I'll give you some links to that a little bit later. But so let's just look, for example, we're going to go back to this vanilla SQL method. We're going to use db get query. We're going to select star from treatments, so give me all the columns from the treatments table. We want to left join with the yields table, and we want the join to be on treatments.plotID, and we want that to match yields.plotID. And so here we've got the first 3 columns, those are from the treatments table, and we've got the second 2 columns, those are from the yields table. And you notice that plot ID gets repeated, which is not ideal, but it is kind of nice to be able to check and make sure that the right thing was copied, the right rows were matched up to each other. The sort of way that I would prefer to do it is to use the dplyr syntax. So here we're just going to use this function left join, and we're going to say give me the treatments table, give me the yields table. And again, both of these are going to return these lazy queries and then perform a left join. So let's see what that does. All right, so again, it shows us that we have a lazy query with an unknown number of rows, that this exists inside the database. And here you notice that we don't have that repeated plot ID column. This can be really fast on the database side if you have some really large complex joins, which we will cover one in the next tutorial series. And then once you've done the join and the database has done the hard work for you, you run collect to pull the database in for further analysis. So we used a left join here. There are all these other types of joins, the full outer cross join, inner joins, right joins, semi-joins, anti-joins. There's a really good help page if you go to the dplyr full join help page. So you can see this has both instructions about the arguments that you need, as well as this nice list of explanations of what the different types of joins do. So let's put all this together into a single query. We're going to do a left join, and we are going to do it on this lazy query between treatments and yields. Then we are going to group the resulting table by crop and tillage, and then we're going to ask for a summary of each group with the mean and the standard deviation. So you can see this is the SQL that's generated. Again, it's starting to get a little bit more complicated, a little bit harder to read, and then this is the table that gets returned right here. And so it's got our mean and our standard deviation, and again, all of that happened inside the database. None of this happened sort of in your local R environment until you tell it that you want to collect it locally. And again, because we are good stewards of our data management, we are going to make sure to disconnect from the database when we're done using it for the session. So that's basically all there is about running a local database. I definitely recommend that you play around with this, see how you might want to change around the code, and then you can just go back up here to the top and run this cleanup chunk and right here, and it will delete everything that you've done so you can start over from scratch. And then in the next series, we are going to talk about talking to the actual PSA on-farm database out in the cloud.